Okay, for the second two problems that you'd asked me about, what was it, number 4 and 5? I think we can work those together. In one of them, the motor is delivering power to the load, and in the other one, the load is actually delivering power back to the motor. And when a load delivers power back to a motor, it actually turns a motor into a generator. But that's another story for a different day. So let's find our equation and see what we can do with working this problem. And I'll start with a screen share here and pause so you don't have to wait for me to get through that. So the two figures that are referenced in that problem are, figure 13 and figure 14. And again, if I'm on the wrong page with this stuff, you guys let me know. But I'm just basing that off of this PDF version of this textbook that I found that I was able to download, and I can upload that to this OneNote and actually draw on it. So that's why it's a little bit different than what you're seeing. But anyway, so figure 13 is a situation where the motor is delivering power to the load, okay? And so that is indicated here with this power designation, right? This. So power is being delivered to the load. So that's one thing that can happen. And then another thing that can happen is that the load can actually deliver power back to the motor. Now that is a fundamental concept of a lot of things that you guys are going to be dealing with, or you may already be dealing with it. A hybrid vehicle actually delivers kinetic energy of rotation and back to the system, and it conserves energy and actually causes a recharge of um, batteries and so forth. But anyway, I'm way out in front of myself. But just trying to let you know that this stuff is relevant to things that we will be looking at. But anyway, so we need an equation for this. And somewhere in this book, there should be an equation for the power of a motor. Is that in here somewhere? There it is. Power of a motor. There it is. The power of a motor is equal to the speed times the torque times 9.55. Okay, so that's what we want to work off of. I think I can even remember that one. And so our particular problem that we're looking at, let's see if I can remember that. It says the torque is 40 Newton meters in number 4, and the speed is 50 RPMs. Okay, what's the power delivered to the motor? Okay, I can do that. Power is equal to speed times torque divided by 9.55. That's a commonly used constant, isn't it? That 30 divided by pi, that helps us work through transitions of SI units to, particularly this deal where we're looking with RPMs, but neither here nor there. We're given the equation. So anyway, our speed is 50. The torque is 40 Newton meters divided by 9.55. And so that should be, for this particular problem, 209 watts. And what that means is that is power that the motor is delivering to the load, 209 watts. All right. Then the other thing he says is a situation where the torque is 40 Newton meters here, same as before, and the speed is 50 RPMs. What is the power received by the motor? Okay, so it's the same calculation, right? It's this, 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 but what he's trying to get us to understand is power flows to and power flows from, and we have to understand the situation And that's really all he's asking us for there. Okay, so that's number 4 and number 5. Both of them work the same way. Questions, let me know, and we'll work these out until you're satisfied that you know it.